here is a physics problem. This one's kind of weird, but also kind of awesome and kind of important. And it's got a lot of stuff in there, but we can do it. So the question says, I have it printed out right here. The sun, our sun, produces a power of 3 times 10 to the 3.9 times 10 to the 26th watts, which is a lot. And the Earth orbits the sun at a distance of 1.5 times 10 to the 11th meters. You may think, why do you care about that? Well, let's get to that. So the question says, if the Earth is tilted, which doesn't really matter right now. So here's the Earth oriented like that. The sun's coming in this way. And I have a point P right there. I have a point R. Oh, wait. I drew this wrong. No, that's right. R. Yeah, I want to find R. This is R. I want to find the power at point R. So this is the point where the sun is directly overhead that way. And it's a 1 square meter solar panel. And let's calculate the power that 1 square meter solar panel receives, assuming it's 100% efficient. Okay, so we've got a bunch of stuff here. The first thing is, if I have the sun producing power at 3.9 times 10 to the 26 watts, what do I do about the energy at the Earth? Well, one thing I could do is to calculate the intensity of light. So remember that the intensity is the power divided by the area. So imagine this area of the Earth's orbit covering the sun. All of the sunlight from that power has to be distributed over that spherical area. And so the area of the sphere is 4 pi r squared. So here I'm going to use this value for r, and that's my area. And so I can calculate I, it's going to be 3.9 times 10 to the 26 watts divided by the area, 4 pi times r squared, which is 1.5 times 10 to the 11th squared. Now, be careful with your calculator, okay? Make sure you're friends with your calculator. I'm going to go ahead and get a numerical value for this because we're going to use it. So I'm going to drop that, and I'm going to enter 3.9 times 10 to the 26, 4 divided by pi divided by, and then 1.5 times 10 to the 11th squared divided by. And I get an intensity of light at the Earth of 1379 watts per meter squared. So that's an important number. I'm going to put it over here so it's out of the way. I equals 1379 watts per square meter. Can you still see that? Yep. Okay. So that's the intensity of light. Now, how much power does the solar panel right here receive? Suppose the light's coming in this way. At that point R, the important thing is that the solar panel is oriented directly perpendicular to the light. So this angle is going to be the angle between the light and the normal, theta equals 0. So power is going to be equal to IA cosine theta. Well, theta is 0, so cosine of 0 is 1. So now I can take the intensity of light times the area of that solar panel, which is 1. So I get the power at that point R is just going to be 1 square meter times 1379 meters squared. So that's the power per square meter for a solar panel. That's the best you can do. And you can't even do that well. Because again, a solar panel is probably like 25% efficient at best for the best solar panels. So if I multiply that by 0.25, I get P real is 344 watts. So if you have a square meter, which is a big solar panel, right? 344 watts in direct sunlight. Now, if you're not at point P on the Earth, you can always tilt that solar panel, right? You always want to tilt that solar panel so that you get theta as small as possible. Okay, next question. What about these points, point P and point S? Would they receive more or less power? We could calculate that. I'm not going to because the question didn't ask for it. But in this case, at that point, light's coming in here. Theta is greater than 0. So when I put in a number greater than 0, cosine is going to be less than 1. So the power here is going to be less. And the power there is going to be even less. And of course, unless, like I said, you tilt it. Okay. So you want that angle as small as possible. Now, actually, if you think about it, there's two things you could do. You could have your solar panels mounted at some angle, some permanent angle. It's cheaper to mount, it's cheaper to install, but you will get less power. Or you could have it actually change its angle and even rotate with respect to where the sun is in the sky, which is a lot more expensive to maintain and to build, but you get more power. So you have to pick, right? Suppose you want to power the entire Earth with solar panels. How much area would you need for your solar panels, assuming that they're 100% efficient? Is that what I said? Yeah, which they're not. Okay. So the Earth uses 15 terawatts, so that's 15 times 10 to the 12th watts. Now we can just calculate the area. It's the same thing, right? So let's calculate the area that we need, and then we'll find out how big that would be square-wise. So I know the power is 15 times 10 to the 12th watts, and that's going to be the power is the intensity is the power over the area. So the area is the power over intensity. So it's going to be power is intensity times area. Yeah, I don't know why I got that wrong. Okay, so I want to solve for the area here. So the area is going to be 15 times 10 to the 12th watts divided by the intensity, 1379 watts per square meter. If I do that, I get an area of 15 times 10 to the 12th, 1379 divided by, I get 1.09 times 10 to the, 2, 4, 6, 8, 10. 10 square meters. So imagine that I make that into a block like that. I know the area, so what's the width and the height? So the width here would just be the square root of that. And I get 1.04 times 10 to the 245. So we could write that as 104 kilometers. That's not that big, right? I mean, for the whole Earth. Now, that actually wouldn't work, because sometimes if you put that on the Earth rotates. It's not always day, but it's possible. You know, even if you think about, okay, well, it's only 10% efficient. Well, then you need 1,004 kilometers, right? It'd be 10 times larger, and so it's still possible to do it. So, okay, that's that problem. The end.